Swayam Prabha. Digital India. Educated India.
Namaskar. So, today we will discuss about the various circuit elements in this lecture. Basically, the major passive elements in our electrical circuits are resistor, capacitor and inductor. So, today we will discuss the various properties of resistor, capacitors and inductors. So, let us start with the first element called resistor. So, let us see what is resistance. So, resistance is a physical property or ability of an element to resist the current. So, basically whenever the current flows in a particular element, it tries to oppose the flow of current. So, that property of that element is called resistance. Now, how you will represent this resistance? The symbol is R. So, you generally will see that in the literature the symbol R is most commonly used for the resistance and it is measured in ohms. Resistance of any material is having dependence on the area as well as length of the element. So, basically if you see cross section of a particular element like this, so this would be your area A and then length. So, the resistance of that particular element is given by rho L by A. It means the rho would be the resistivity of the material, which is represented in ohm meters, and then the length of the element and cross sectional area of that element. So, these two properties of that element with the resistivity of the material will define what is the value of resistance of that element. So, in common circuit elements, resistance is one of the most common, and you will see that in the various literature and books you will see this kind of figure represented for the resistance. Now, how the resistance property came into the literature? George Simon Ohm was the German physicist who developed the relationship between current and voltage for a resistor, or this relationship is called as Ohm's law, which was given by the that German physicist. Now, what Ohm's law says? Ohm's law says that the voltage V across a particular resistor is directly proportional to the current I which is flowing through that resistor. So, you can simply represent that V is directly proportional to current I. Now, Ohm defined one constant which is called proportionality constant for this particular equation, and that was represented by R, and from there the equation came like V is equal to R into I. So, this proportionality constant was the resistance of that element through which the current is flowing. So, now from the above equation you can simply say that resistance R is nothing but voltage V divided by current. So, for 1 ohm what you will say? You will say 1 ohm is nothing but 1 volt per ampere. Now, the value of resistance R can change from 0 to infinity. Now, if the resistance value is R is 0, it means that that particular element is short circuit. So, ideally if you take electrical wire, you assume that the value of R is 0, because if you connect that wire through between two nodes, then the two nodes will be short circuited. So, that is basically the ideal condition, because in practical scenario all electrical wires have their own resistance. although it is small as compared to the other resistive elements, but it is still need to be considered. But under ideal condition we assume that the value of that element is 0. So, when the value of R is 0, we generally call it as a short circuit condition. So, what will happen under short circuit condition? The value of V, that is IR, will be equal to 0. So, it means that under short circuit condition the voltage across the element would be 0. Similarly, if the value of R is infinity, because R can range from 0 to infinity. So, under next boundary condition, that is R is equal to infinity, you will consider the circuit as open circuit. Under that open circuit condition, what would be the current I? You can find out the value of I is nothing but limit R tends to infinity V by R, and the value of this is equal to 0. So, it means that under open circuit condition the current flowing through that element would be 0. Now, another useful element in the circuit analysis is reciprocal of the resistance, which is known as conductance and represented by capital G. Now, it is defined as a measure of how well an element can conduct the electric current. So, it is just opposite to the resistance R. R is nothing but the property of any element to resist the flow of current, while conductance says that how well that particular element can allow the flow of current. So, the unit of conductance is given in Siemens, or alternatively you can say as mho. Mho is nothing but the opposite of ohm. So, if you write ohm in a opposite fashion, it will become mho. So, it is just easier for you to understand or to remember also that the mho is the dimension for the conductance. Now, it can be expressed mathematically as G is nothing but 1 by R. So, what will happen since R is nothing but V by I, so G will become I by V. So, that is why the G is represented as opposite of resistance R. So, the conductance now can be expressed as 1 Siemens or 1 mho is nothing but 1 ampere per volt. Now, same resistance can be expressed in terms of ohm or resistance, ohm or Siemens. That means, if one resistance is having 10 ohm as a resistance, in the same way you can say that that element is having 0.1 mho as a conductance. Now, let us see how you will calculate the power dissipated in a resistor. The power dissipated in resistor can be expressed in terms of the elements like resistance R and the voltage and current. So, now in first lecture we derived the equation of power, that was P is equal to V I. Now, from Ohm's law what we got? We got V is nothing but I into R. So, if you combine these two, you will get the value of power P is nothing but V into I, or you can write as I square R, or alternatively you can write V square by R. So, alternatively the power dissipated can also be expressed in terms of conductance. So, wherever you see R, you just replace R by R with 1 by G, you will get the value of power P in terms of conductance. So, in this case what will happen, the power P, that is V I, that is power P is nothing but V I is equal to V square G or I square by G. Now, let us take an example to understand better the theory which we just discussed. That is, suppose a 30 volt voltage is applied across a resistor of resistance 5 kilo ohm. Calculate the current, conductance and power absorbed by the resistor. So, here the voltage across the resistor V is 30 volt then the current I would be V by R. So, you just put the value of V and R, you will get the current output as 6 milliampere. Now, what would be the conductance? The resistance R is given. So, you just take 1 by R of the value given, you will get the value of conductance, that is 0.2 millisiemens or millimho. Now, let us try to find out the power dissipated or absorbed by the resistor. You can use any formula which we have discussed till now. Let us take one formula like P is equal to V I. So, when you put the value of V and I, you will directly get the value of power dissipated, that is 180 milliwatt. Similarly, P can also be represented as I square R. So, put the value of current I. So, I square into R, if you put the value, again you will get the same value of power dissipated, that is 180 milliwatt. Now, third option is that you can calculate with the help of conductance, that is P is equal to V square G. Put the value, you will again get the value of 180 milliwatt. So, you can use any formula which you want to use for calculation of power, you will get the same value eventually. Now, let us take another example. Suppose if the voltage source of 20 sin pi t volt is applied across the resistor of resistance 5 kilo ohm, how you will calculate the current through the resistor and power absorbed by the resistor? Simply use the formula I is equal to V by R. You put the value of V and R, you will get the value of current I. So, here the voltage V is sinusoidal voltage. So, that is why it is 20 sin pi t. If you divide by resistance R, you will get current as 4 sin pi t milliampere. Now, to calculate the value of power P, P is nothing but V I. So, this power P would be instantaneous power, because we are using instantaneous voltage and current. So, you just simply use voltage V, that is 20 sin pi t, and then multiply with the current which you calculate, that is 4 sin pi t, and you will get the output as 80 sin square pi t milliwatt. Now, let us come to the other element called capacitance. Let us try to understand what is capacitor. So, capacitor is a passive element designed to store energy in its electric field. So, capacitor is typically constructed using two conducting plates separated by an insulator or dielectric. Now, when you apply voltage V across the plates of the capacitor, a charge Q is deposited on one plate of the capacitor and charge minus Q is deposited on the other plate of the capacitor. So, therefore, you can say that capacitor is an element which stores charges. Now, what would be the amount of charge stored? That would be directly proportional to voltage V. So, you can say that Q, that is stored charge, is directly proportional to V. Now, you can introduce another proportionality constant, that is called C. Okay. So, here what is C? C is the constant of proportionality which is known as capacitance of that capacitor, and this C is represented like this. So, for that you have to just put two parallel lines and then connect it. So, these two parallel lines represent the plates of the capacitor and these are the connectors. So, how you will define capacitance now? Capacitance can be defined as the ratio of charge on one plate of the capacitor to the voltage difference between the two plates. So, earlier we saw Q is nothing but C into V. So, C would be Q by V. So, it means the ratio of charge on one plate of the capacitor to the voltage difference between two plates. Now, it is measured in farads. What is the value of 1 farad? 1 farad is nothing but 1 coulomb per volt. So, you can see from here 1 farad is nothing but Q is measured in coulomb. So, 1 farad is nothing but 1 coulomb per volt. Now, capacitance of a capacitor also depends upon its physical dimension. So, if you see the capacitor plates, like if it is 2 plate capacitors, so the area A and the distance between 2 plates also define the value of capacitance of that capacitor. So, how you will define capacitance C? C would be epsilon A by D, where A is surface area of each plate of the capacitor and D is the distance between 2 plates. Now, what is epsilon? Epsilon is the permittivity of the dielectric between these plates and it is measured in farad per meter. Okay. And permittivity of the free space is given as 8.85 into 10 to the power minus 12 farad per meter. Now, to obtain current voltage relationship in a capacitor, we can use the equation I is equal to dq by dt. This is what we calculated in our first lecture, and then q is equal to Cv, which we just now saw. So, if you use these two equations, you can find the value of current I. So, what you have to do? You have to simply take the derivative of both sides of the equation with respect to time. So, this will become dq by dt equal to C dV by dt. C is a constant. So, you cannot differentiate. If you differentiate, it will become 0. So, dq by dt is nothing but C dV by dt. What is dq by dt? I. So, what you get? C dV by dt. So, you can easily calculate the value of current I for capacitor. Now, if you are asked to find out the instantaneous power, then you have to simply multiply the current which you calculate previously with V, you will get Cv dV by dt. Now, how to calculate the energy stored in the capacitor? You have to just integrate over the time of this power, you will get the value of total energy stored. So, what would be the value? You integrate from minus infinity to time say t at particular instant where you want to find out the value of energy stored, then this is p tau d tau. So, C is constant, you can take it out, minus infinity to t V dV by d tau and multiplied by d tau. So, what will happen? These two will cancel out. So, eventually your differential would be with respect to dV. So, your limits now will change from V from minus infinity to V at time is equal to t. So, this will come out to be half Cv square. Now, at infinity you will assume that capacitor is fully discharged. So, it means that your value of V at minus infinity would be 0, and if you take value of Vt V at time at particular time t, then you will say simply as V. So, your total value of power energy Q W would be half Cv square, or alternatively you can write Q square by 2C, because Q is nothing but C into V. So, using that particular formula also you can find out the value of energy W in terms of Q and C. So, now this equation represent energy stored in the electric field that exists between the two plates of the capacitor. So, this energy can be retrieved because it is an ideal capacitor. So, it will not dissipate energy by itself. So, that is why you can say that capacitor is elements capacitance having the capacity to store the energy in its electric field. Now, when the voltage across the capacitor is not changing with respect to time, the current through the capacitor would be 0. That means, the capacitor acts like an open circuit for a DC voltage. Now, take one example. Let us calculate the charge stored on 3 picofarad capacitor with 20 volt applied across it. You just simply use the formula Q is equal to CV and you will calculate the value of Q. Now, energy stored, you will use W is nothing but half CV square, put the value, you will get the value of energy stored, that is 600 picojoule. Now, if the voltage across a 5 microfarad capacitor is sinusoidal, that is Vt is equal to 10 cos 6000 t volt, how you will calculate the current passing through it? You have to use the formula I t, that is nothing but C dV by dt. You differentiate V with respect to time and put the values, you will get current output as minus 0.3 sin 6000 t ampere. Now, if you are asked to determine the voltage across 2 microfarad capacitor, if the current through it is like 6 e to the power minus 3000 t milliampere, assume initial capacitor voltage to be 0. So, what will happen? You have to use V t is nothing but 1 upon C integral 0 to t I dt. So, how you got this? Since you know I is equal to C dV by dt, if you take dt as this side, so it will become dV is nothing but 1 upon C I dt. So, if you integrate on both sides, you will get V is nothing but 1 upon C is constant, you can take it out into I dt. So, this particular value V we have utilized to find out the voltage across the capacitor. Now, we are assuming that initial condition V 0 is 0. So, you have to just simply integrate for I dt. I value is given. If you put the value and integrate, you will get the value of voltage V as 1 minus e to the power minus 3000 t volt. Now, let us come to the third element, that is inductance. Now, inductor is another passive element which is designed to store energy, but here the stored energy is in the form of magnetic field. Inductor consists of coil of conducting wire, and current, when current is allowed to pass through an inductor, it is found that the voltage across the inductor is directly proportional to time rate of change of current. So, that means voltage is proportional to di by dt. So, now if you convert into equality, V will be L di by dt. So, this proportionality constant is nothing but the inductance of that element through which the voltage is measured and current is changing with respect to time. So, this V is nothing but L di by dt is the property of the inductor, and how you will represent this? This is represented in the form of a coil. So, symbol you will see in the literature like this, which is nothing but the symbol for inductor. Now, inductance is what? Inductance is the property whereby an inductor exhibits opposition to the change of current flowing, and it is measured in henries. So, what is 1 Henry? 1 Henry is nothing but 1 volt second per ampere. So, this you can easily correlate with the value L di by dt. So, L would be like, if you write in small time step fashion, you can simply write V delta t by delta I. So, voltage is in volt, t is in time second, and I is in ampere. So, you can simply say that 1 Henry is nothing but 1 volt second divided by ampere. So, inductance of an inductor depends upon the physical dimensions also. So, suppose if you have a coil like this and you are asked to find out the value of inductance. See, coil will have some its own cross sectional area. So, if let us say it is A and length is L. So, for this type of inductor, your inductance value would be L n square mu A by L. N is the number of turns. So, you see we have made number of turns over here. So, capital N is nothing but number of turns, A is the cross sectional area, L is the length of the inductor, and mu, what is mu? Mu is the permeability of the core of the inductor. So, with this you can calculate the value of L, that is n square mu A by. So, L is that is capital L is generally the symbol we use for presentation of inductor, and small l is the length of the inductor. So, now what you can write? You can write d I is nothing but 1 upon L V dt, because we just now saw that V is nothing but L d I by dt. So, using this you can also write d I is nothing but 1 by L V dt. So, to find out the power delivered to the inductor, you will write P is nothing but V I, V you replace with L d I by dt and current I. So, if you are asked to find out how much energy has been stored in a inductor, so it is inductor not capacitor. W is nothing but minus infinity to t p tau d tau, L that is again minus infinity to time t, because let us say we are trying to find out the value of energy stored at time t. You replace the value of p from here. So, that will become I d I by d tau, and if you integrate you will get half L I square, and the current changing current limits are from minus infinity to any time t. Now, at the initial condition we assume that t at minus infinity the value of current is 0. So, finally, what we get? We get the total energy stored is half L I square. So, above equation represents the total energy stored in the magnetic field of an inductor. So, opposite to what we saw in the capacitor, capacitor stored energy in the electric field, but the inductor stored energy in the magnetic field. Now, voltage across an inductor is 0. It means that current through inductor is constant, because V is L d I by dt, V is 0 means rate of change of current is 0. So, voltage across inductor would be 0. In that case, the inductor would act like a short circuit to DC. Now, important property of this inductor is that it will oppose to the change of flow of current through that particular element. So, it means that you can say that current through an inductor cannot change abruptly. Therefore, the ideal inductor would like an ideal capacitor cannot dissipate energy, and it will store energy which can be retrieved at a later time. So, now let us take one example. Suppose if the current through an inductor is needs to be like it is given I t is equal to 10 t e to the power minus 5 t, and the inductor value is 0.1 Henry. We need to find the voltage across that inductor. So, what we will do? We will use the formula, that is V L d I by dt. The value of L is given. Simply differentiate the current equation, that is d by dt of 10 t e to the power minus 5 t. So, when you will differentiate, you will get e to the power minus 5 t plus t times minus 5 into e to the power minus 5 t. So, finally, what you will get voltage V? V is nothing but e to the power minus 5 t into 1 minus 5 t volt. Now, if you are asked to find out the value of energy stored in an inductor, you simply use formula W is nothing but half L I square. So, you just put the value of inductance which was given in the question, and then the value of current I which is given. So, finally, what you will get? You will get 5 t square e to the power minus 10 t joule, which is the total energy stored in that inductor. So, today we saw three basic elements of our electrical circuit, that are resistor, inductor and capacitor. So, we also saw that the property of these three elements, and also saw what is the Ohm's law. So, in next lecture we will try to find out how you will utilize this knowledge in analyzing the circuits. So, thank you very much